It begins not with a bang, but with a shimmer, a sudden streak of light that slices across the black velvet of space. For a fraction of a second, it looks beautiful. Then it disappears. Moments later, a tremor ripples through the atmosphere, and on the ground, instruments thousands of miles apart begin to twitch. The signal is faint, but unmistakable. Something massive has just passed terrifyingly close to Earth. For most of human history, the night sky has been our companion, our calendar, our compass. We learned to read its constellations long before we learned to write our own stories. But hidden among those familiar stars are the drifters, fragments of rock and metal, some no bigger than a car, others the size of mountains. Each one is a relic from the birth of our solar system 4.5 billion years ago. And each one moves silently, waiting for the wrong trajectory, the wrong pull of gravity, the wrong moment. Every year, astronomers scan the heavens, tracking over 1 million near-Earth objects, asteroids and comets that occasionally brush our orbit. Most are harmless, a few are not. Every few centuries, one comes close enough to remind us how fragile our world really is. Around 66 million years ago, one such visitor ended the reign of the dinosaurs. It struck with a force equivalent to billions of nuclear bombs, igniting forests, boiling oceans, and turning the sky into fire. It was extinction on a planetary scale. But that was ancient history, wasn't it? In the high deserts of Arizona, there's a mile-wide scar in the ground meteor crater. The asteroid that made it was barely 130 feet across, about the size of a small jet plane. Yet the explosion released as much energy as a large nuclear weapon. Everything within miles was vaporized. That was 50,000 years ago, and according to NASA's current data, there are tens of thousands of objects that size still crossing Earth's path today. What happens if one doesn't miss? The story you're about to hear begins as a series of scattered clues, strange mineral fragments in the bones of ancient animals, layers of burned soil buried deep beneath the ice, and a mysterious black line in the Earth's crust that marks the sudden disappearance of entire species. For decades, these anomalies puzzled archaeologists and geologists alike. But recent discoveries have begun to connect them, revealing a chilling possibility. That smaller, unrecorded asteroid impacts may have reshaped the course of human history. Not once, but many times. We like to think of asteroid strikes as once-in-a-lifetime events, freak accidents of cosmic chance. But the evidence suggests something far more unsettling. Impacts happen regularly, we've simply been lucky. In 1908, a small asteroid exploded over the Siberian wilderness of Tunguska, flattening 60 million trees across 800 square miles. If that same explosion had occurred over New York, London, or Tokyo, millions would have died. In 2013, a meteor less than 60 feet wide streaked across the Russian city of Chelyabinsk. The shockwave shattered windows and injured over 1,500 people. That rock weighed only about 10,000 tons, practically a pebble by cosmic standards. What would happen if the next one were just a little larger? This question has ignited one of the most urgent scientific efforts of our time, to find every potential killer in the sky before it finds us. The U.S. Space Guard Survey, led by NASA, has cataloged over 1,000 planet-killer asteroids, those at least half a mile wide, capable of ending civilization. But beyond them lies a swarm of smaller, deadlier threats. Objects just 100 feet across, invisible until days before impact, could still destroy an entire city. And then, in 2004, astronomers detected something that froze their blood. An asteroid, roughly 900 feet wide, was moving directly toward Earth. It was named Apophis, after the Egyptian god of chaos. Initial projections suggested a possible impact in the year 2029. For weeks, scientists around the world scrambled to verify the numbers. Would this be the one? The answer, not yet. Apophis will pass just 18,000 miles from Earth's surface, closer than many satellites. A near miss, this time. But that wasn't the only revelation. As scientists probed deeper into the solar system, they discovered something unexpected on another world. A spacecraft named Cassini, orbiting Saturn, captured evidence that could rewrite the story of life itself, and perhaps our understanding of extinction. Beneath the frozen crusts of Saturn's moons Titan and Enceladus, Cassini found vast oceans of liquid water, heated by the same forces that tear planets apart. And in those dark, alien seas, it found the chemical building blocks of life. The same chaos that destroys worlds might also create them. Meanwhile, back on Earth, our planet faces a quieter, invisible threat. High above the South Atlantic, Earth's magnetic shield, the force that protects us from solar radiation, is weakening. Satellites passing through this South Atlantic anomaly are bombarded with deadly particles. Our planet's magnetic field is fading faster than ever before. Without it, the atmosphere would erode, oceans would evaporate, and life, at least as we know it, could not survive. From the fall of the dinosaurs to the rise of humanity, from the frozen moons of Saturn to the vanishing strength of our own planet's heart, a single thread connects them all: the fragility of worlds and the power of cosmic events to erase everything we think is permanent. So tonight, as the stars drift quietly above us, remember, one of them might not be a star at all. It could be a stone, cold and ancient, tumbling silently through space, carrying the memory of 1 billion years. And maybe, just maybe, it's coming home. Part 1. The first signs. When the sky fell twice, the first sign didn't come from space, came from the ground. In the dry deserts of northern Arizona, geologist Eugene Shoemaker once stood on the rim of a vast, circular pit, around a mile wide and 570 feet deep, surrounded by shattered rock. Locals called it Meteor Crater. For decades, scientists thought it was a volcano. But Shoemaker saw something different. Sandstone fused into glass, iron melted by heat hotter than any earthly furnace. He realized that 50,000 years ago, a rock no bigger than a small jet plane had slammed into Earth at over 50,000 miles per hour, releasing energy equal to a large nuclear bomb. It was the kind of revelation that changes how you see everything. Because if something that small could wipe out a desert, what could a larger one do? Fast forward to the present day. The crater still glows orange in the sunrise, its edges sharp like a warning carved into the planet's skin. Visitors take photos, scientists collect samples, and astronomers look up at the sky, not out of wonder, but of fear. For in the vast silence of space, the same kind of rocks still roam, invisible until it's too late. And then came another clue, not from a crater, but from something alive. In the frozen tundra of Alaska, fossil hunters unearthed the tusks of ancient woolly mammoths. At first glance, they seemed ordinary, enormous spirals of ivory, preserved in permafrost for tens of thousands of years. But under a microscope, something strange appeared. The tusks were peppered with microscopic impact particles, tiny bits of iron and nickel fused into the bone like buckshot. These were not the scars of hunting or decay. They were fragments of a meteorite blast. Dr. Richard Firestone, a physicist turned archaeologist, studied them closely. The composition matched that of known meteorites, rich in iron, nickel, and rare isotopes found only in extraterrestrial materials. It was proof that these mammoths, 34,000 years ago, had died in the aftermath of a cosmic explosion. But if mammoths perished under a rain of fire, what about the humans who lived beside them? 1,000 miles to the south, in the limestone caves of Ohio, archaeologist Ken Tankersley found his answer. Beneath 30 feet of earth, his team uncovered a thin, black layer of carbonized soil. It was rich in soot and melted glass, the kind of residue formed when extreme heat flashes across a landscape. Tankersley called it the black mat. Beneath it, fossils of mammoths and giant sloths. Above it, none. In one layer of soil, the record of life simply stopped. At the same time, the Clovis culture, one of North America's earliest human societies, vanished from the archaeological record. No evidence of warfare, no epidemic, just sudden silence. Tankersley was puzzled. The black mat stretched across multiple sites in North America, each dating to around 13,000 years ago, the same time the Clovis disappeared. Chemical analysis revealed traces of iridium, a metal rare on Earth but common in asteroids. There were also nanodiamonds, microscopic crystals formed only under immense pressure, like the detonation of a cosmic impact. Could it be that an asteroid had struck the continent, vaporizing everything in an instant, and left no crater behind? To answer that, scientists turned to the past, and to one of the strangest craters on Earth. In Siberia, deep within the swampy forests of Tunguska, lies a scar that doesn't exist. On June 30, 1908, something exploded in the sky. The blast leveled 60 million trees across 800 square miles, an area larger than London. Witnesses hundreds of miles away reported seeing a blinding light, brighter than the sun. Yet when researchers arrived years later, there was no crater. The asteroid had detonated in mid-air, releasing the energy of 1,000 atomic bombs. For decades, scientists estimated that the Tunguska asteroid was roughly 600 feet wide, big enough to destroy a small nation. But new computer models tell a different story. It may have been only 100 feet across. That means there are far more like it, and they hit far more often. In geological terms, that's a terrifying statistic. Because if Tunguska-sized asteroids strike Earth every few hundred years, then we are overdue. And if the Clovis event really was another Tunguska, one that exploded over the North American ice sheets, it could explain everything. The ice would have absorbed the shock wave, melted, and then refrozen, erasing all signs of a crater. But the heat, the pressure, and the firestorm would have been enough to wipe out an entire species, or an entire culture. To test this, Professor Peter Schultz at NASA's Ames Research Center built a simulation using a vertical gun, a device capable of firing projectiles at 13,000 miles per hour, mimicking an asteroid's impact velocity. His team shot glass beads into blocks of ice. The results were startling. The impacts generated massive fireballs, yet left no visible crater. When the ice melted, all evidence of the impact vanished, like a crime scene washed clean. Schultz called it a perfect cosmic crime. The idea was both thrilling and horrifying. If a half-mile wide asteroid could strike an ice sheet, obliterate everything within hundreds of miles, and leave no trace, then history might be full of forgotten catastrophes. Impacts we never knew happened, buried under time and geology. And maybe one of those catastrophes changed the course of civilization. Because when the Clovis vanished, so did many of the megafauna of North America. Mammoths, mastodons, saber-toothed cats, and giant ground sloths. It wasn't gradual extinction. It was instantaneous. The timing was too perfect to ignore. Today, scientists still debate whether the Clovis people were victims of a cosmic impact or of changing climate. But the evidence continues to grow. Across dozens of sites in the US and Canada, that same thin line of carbon and ash runs like a scar through the soil, the fingerprint of an apocalypse. And perhaps the most unsettling discovery is that the pattern repeats. Every few thousand years, layers of soot, melted rock, and iridium-rich debris appear again. The sky falls, the earth burns, then silence. Our planet, it seems, has a long memory of destruction, and it keeps repeating the same warning. This will happen again. The question is not if, it's when. Because right now, as you listen to this story, there are more than 30,000 near-Earth objects hurtling through space. Most are harmless, but some are not. The smallest could flatten a city. The largest could end humanity. And the one we never see coming, that's the one that keeps astronomers awake at night. In the next chapter, we'll follow the scientists who have dedicated their lives to finding these silent killers and learn how humanity might fight back against the oldest enemy in the cosmos. Part 2. Tracking the Killers. How we watch the sky. In a dark observatory high above the Arizona desert, for faint dots drift across a computer screen. To most eyes, they're meaningless, just another patch of stars. But to Ed Bescher and his team at the Catalina Sky Survey, those 4 dots are the difference between a quiet night and a planetary emergency. They run the SpaceGuard survey, A global effort launched in 1998 after the U.S. Congress ordered NASA to find 90% of all near-Earth asteroids larger than 1 kilometer. These are the planet killers, rocks big enough to turn entire continents into wastelands. The mission is simple but daunting. Find them before they find us. The telescope scans the sky 4 times over 40 minutes, taking a series of long-exposure images. The stars remain fixed, but every so often one tiny point shifts. That motion means only one thing. It's not a star. It's an intruder. Escher points to the screen. "See that?" he says quietly. "That one's moving." The discovery seems routine, but each new object sets off a chain of calculations. Within minutes, computers around the world start crunching the data, estimating its orbit, speed, and distance. Astronomers from observatories in Chile, Spain, and Hawaii log in to confirm the sighting. The numbers bounce between time zones faster than the asteroid itself. The next step is always the same. Will it hit Earth? Sometimes the answer is no. Sometimes it's not yet. When the first catalog was made in the late 1990s, scientists knew of only a few hundred near-Earth asteroids. Today, there are tens of thousands. And with every new discovery comes the same realization. The smaller the asteroid, the harder it is to see, and the more dangerous it becomes. Large asteroids, a mile wide or more, are rare. They hit Earth perhaps once every 75 million years. But those around 100 to 300 feet wide, small enough to evade most telescopes, large enough to destroy a city, strike every few centuries. These are the ones that haunt the nightmares of planetary scientists. "We found the big ones," says Rusty Schweikart, a former Apollo test pilot and one of the founders of the B612 Foundation, an organization dedicated to planetary defense. "Now we're hunting the ones that can still ruin your day." He isn't joking. Schweikart compares the problem to insurance. You and I drive cars knowing there's a 1 in 10,000 chance we'll have an accident tomorrow. But we still buy insurance because that one chance is enough. He pauses, eyes narrowing. Earth is driving through the solar system totally uninsured. That lack of protection nearly turned catastrophic in 2004. It started as a routine night at the Kitt Peak Observatory. A telescope picked up a faint, fast-moving speck of light. When researchers plotted its trajectory, their blood ran cold. The object was Apophis, a 900-foot asteroid, roughly 10 times the size of the rock that made Meteor Crater. Early calculations showed a disturbing possibility. It could strike Earth on April 13, 2029. For a brief, terrifying week, the odds of impact were calculated at 1 in 37. Newspapers called it the asteroid that could end civilization. NASA convened an emergency task force. Dr. Richard Binzel, a planetary scientist at MIT, spent sleepless nights recalculating Apophis's orbit. An impact of that size would be regionally catastrophic, roughly the size of France, maybe larger. You don't sleep much when the math points to that. Apophis weighs 20 million tons, mostly composed of a dense rock called chondrite, the same material found in meteorites that occasionally crash through Earth's atmosphere. If it hit, it would release 375 megatons of energy, 20,000 times the blast at Hiroshima. As more data came in, the orbit shifted just slightly but enough. On April 13, 2029, Apophis will pass only 18,000 miles from Earth's surface, closer than our geostationary satellites. In cosmic terms, it's a hair's breadth. A near miss this time. But what if it hadn't missed? What could we have done? For decades, the most obvious answer was also the most dangerous. Nuclear weapons. In theory, detonating a bomb near an asteroid could blow it apart or push it off course. But the risks are staggering. A poorly timed explosion could fragment the rock into radioactive shrapnel, turning one impact into thousands. A cosmic shotgun blast, one scientist called it. Others proposed more elegant solutions. Attach rocket engines to the asteroid and gently push it away. Or use solar sails to nudge it into a safer orbit. Brilliant ideas, but mostly theoretical. The European Space Agency proposed something more practical. A mission called Don Quixote. The plan? Hit an asteroid on purpose. The spacecraft would consist of two parts, an impactor and an orbiter. The orbiter would track and photograph the target. Then the impactor would slam into it at high speed, delivering a precise, controlled shove. Even a tiny change in velocity, less than a millimeter per second, could, over years, cause the asteroid to miss Earth by thousands of miles. Chris Saunders, a mission analyst on the project, explained it simply. It's like a game of cosmic billiards. You don't need to smash the ball apart. You just need to nudge it a little early. The Don Quixote project never launched, but its ideas lived on. In 2022, NASA's DART mission successfully crashed a probe into the asteroid Dimorphos, changing its orbit by 33 minutes. It was the first real-world proof that humanity could deflect a celestial body. For the first time in history, the phrase planetary defense wasn't science fiction. But as with all victories in space, success came with humility. Because the DART test targeted an asteroid only 525 feet wide, barely 1/10 the size of Apophis. It worked because we had years to plan. If the warning time had been months or weeks, the outcome might have been very different. And there's another, darker truth. The smaller the asteroid, the less warning we get. Many of the objects capable of wiping out a city would appear in our telescopes only days before impact, if at all. The Chelyabinsk meteor proved it. On February 15, 2013, a 60-foot rock exploded over Russia with the energy of 30 atomic bombs. No one saw it coming. The shockwave shattered glass across 6 cities and injured 1,500 people. It entered the atmosphere from the direction of the sun, blinding every telescope that could have seen it. That event changed everything. Since then, planetary defense has become a race against time. New infrared telescopes are being designed to spot asteroids coming from the sun's glare. The NEO Surveyor, a dedicated space telescope, will soon join the hunt. Private observatories, AI-driven sky trackers, and even amateur astronomers have become part of the defense network. Humanity is, for the first time, learning to look up together. But no system is perfect. The solar system is vast. The rocks are countless. And space, as the old saying goes, is under no obligation to warn us. For every Apophis we find, there may be 10 more hidden in the glare, waiting for their turn. And as one NASA scientist dryly remarked, statistically, the next Tunguska isn't a question of if. It's a question of which city. Part 3. The Unseen Threat. When small asteroids turn deadly. In the vastness of space, the big rocks are easy to fear. They make for good headlines, extinction-level impacts, planet killers, Hollywood endings. But scientists have learned that the most dangerous asteroids aren't the biggest ones. They're the small ones, the silent, invisible wanderers, too faint for telescopes, too unpredictable to track. The ones that slip through unnoticed until the sky itself catches fire. It's the quiet ones that kill. Every day, Earth is bombarded by over 100 tons of cosmic debris. Most of it burns up harmlessly in the atmosphere. Meteors, shooting stars, a nightly light show. But every so often, something larger survives the fall. A rock the size of a car can explode with the force of a tactical nuke. A boulder the size of a bus can flatten a city block. And anything above 100 feet across, well, that's enough to erase a city from the map. The nightmare scenario isn't the 10-mile-wide asteroid that wiped out the dinosaurs. It's the 150-foot rock that no one sees coming. Imagine it. A Tuesday morning, cloudless sky, commuters sipping coffee, a sudden flash brighter than the sun. The air ignites, windows shatter, shockwaves race through the streets. In less than a second, the blast releases more energy than a hydrogen bomb, and the city ceases to exist. And the worst part? There would be no warning. That's not science fiction. It's physics. In September 2007, a group of Peruvian villagers saw something strange streak across the afternoon sky, a trail of fire that seemed to be falling from the heavens. Moments later, a thunderous explosion rocked the highlands near the village of Carancas. When the dust settled, a crater 50 feet wide smoked in the desert air. First, no one believed it. A meteor that small, a mere 6 feet across, should have burned up long before reaching the ground. Local officials thought it was a hoax, or maybe a crashed aircraft. But when scientists arrived, led by impact specialist Peter Schultz, the truth was far stranger. Schultz found the soil overturned and fused into glass, fragments of rock scattered across hundreds of feet. He used a magnet to lift metallic grains from the dirt, tiny bits of nickel iron, the calling card of a cosmic visitor. Under the microscope, the fragments told their story. They had entered Earth's atmosphere at 4 miles per second, almost 5 times faster than a rifle bullet. And somehow they made it through. That single impact, caused by an asteroid no larger than a refrigerator, threw 100 tons of soil into the air. The blast was small by astronomical standards, but powerful enough to destroy a city block and kill anyone nearby. If that same object had exploded over Manhattan, it could have shattered glass across the skyline and sent shockwaves through 5 boroughs. Schultz was stunned. "This shouldn't have happened," he said. "That rock was far too small to survive atmospheric entry." But it did. And it hit hard. It was a cosmic curveball, one that forced scientists to rethink everything they thought they knew about asteroid impacts. If a 6-foot rock could do that much damage, then Earth's vulnerability was far greater than anyone realized. The data was unsettling. Statistically, there are millions of asteroids under 100 feet wide orbiting near Earth. We track only a tiny fraction. Most are invisible, lost in the glare of the sun or buried among the stars. On any given day, a few pass between us and the moon, close enough to hit if the gravitational math had been just slightly different. In 2008, one of those rocks did hit, but for once we saw it coming. The asteroid was designated 2008 TC3, a small object discovered by astronomers just 20 hours before impact. It entered the atmosphere over Sudan and exploded with the energy of a medium-sized bomb. When scientists recovered fragments in the Nubian desert, they found something remarkable. A porous, fragile meteorite, the kind that should have disintegrated long before reaching the ground. Yet somehow it didn't. That impact was both reassuring and terrifying. Reassuring because it proved our detection systems worked, at least sometimes. Terrifying because it underscored how little time we'd have to act. The odds of being hit by a large asteroid are minuscule. But the odds of being hit by a small one, they're inevitable. "Think of it like earthquakes," said planetary scientist Mark Boslow, who reanalyzed data from the 1908 Tunguska explosion. "The big ones are rare, but the small ones happen all the time. You don't prepare for the 1-in-a-million event. You prepare for the one that's guaranteed to happen." Boslow's work changed everything we thought we knew about Tunguska. Using advanced simulations, he discovered that the asteroid may have been half the estimated size, only about 100 feet wide. That meant impacts like Tunguska's could happen 10 times more often than previously believed. Suddenly, history looked different. If Tunguska-scale blasts occur every few hundred years, then humanity has simply been lucky for the past century. The next one could arrive tomorrow or tonight, and there might be nothing we could do to stop it. In 2013, that near miss finally came. At 9:20 a.m. on February 15th, residents of Chelyabinsk, Russia, saw a blinding white light streak across the sky. Seconds later, a shockwave shattered windows across 6 cities. The blast wave knocked people off their feet, tore roofs from buildings, and injured 1,500 people. Security cameras captured the event in chilling detail. The fiery trail, the expanding plume, and the delayed, concussive boom that rolled across the snow-covered streets. The Chelyabinsk meteor was just 59 feet wide. It exploded in the atmosphere with the force of 30 Hiroshima bombs. And once again, no one saw it coming. The lesson was devastatingly clear. Humanity wasn't prepared for small asteroids. Not technologically, not politically, not even psychologically. We've always looked up at the night sky and assumed it was still, safe, eternal. But the truth is, Earth orbits through a cosmic shooting gallery, and every bullet is made of stone and iron. Scientists are now building systems to catch these invisible threats. A network of infrared telescopes, radar arrays, and machine learning programs designed to scan the heavens for flickers of movement. But the challenge remains immense. Because for every asteroid we detect, there are thousands we miss. And for every one we miss, the countdown begins anew. Somewhere out there, in the silent cold between Mars and Earth, a rock no bigger than a house may already be on its way. No light, no warning, just a faint shadow moving against the stars. It could be 10 years away, or 10 hours. And if history has taught us anything, it's this. When the sky falls, it doesn't knock first. Part 4. Echoes from the Past. The Hidden Impacts in Earth's History. History, it turns out, is written not just in books, but in craters. The Earth wears its scars like faded tattoos, each one a memory of fire, shock, and extinction. To a geologist, every crater is a sentence in the planet's autobiography, a record of the moments when the sky fell and everything changed. But many of those sentences are missing, erased by time, erosion, and the restless churn of continents. Still, the survivors tell a story, and it's darker than we ever imagined. The first chapter begins in what is now South Africa, deep beneath the gold-rich plains of the Vredefort Dome. It's not just the oldest known impact site on Earth, it's also the largest. Around 2 billion years ago, a rock nearly 10 miles wide slammed into the planet, punching a hole over 190 miles across. The energy released was equivalent to 1 billion nuclear bombs. The impact vaporized entire mountain ranges and altered the chemistry of Earth's crust forever. Life at the time consisted mostly of microbes, but even they felt it. The skies filled with ash, the oceans boiled, and sunlight disappeared for years. Some scientists believe this event may have changed Earth's atmosphere permanently, tipping the balance of oxygen and paving the way for future evolution. In a grim twist, destruction created the conditions for life to flourish. That theme repeats throughout geological history. Each act of cosmic violence somehow seeds renewal. Fast forward 1.8 billion years. The continents have shifted. Dinosaurs rule the Earth. And somewhere above the Caribbean Sea, another giant approaches. The Chicxulub impact is perhaps the most famous catastrophe in Earth's history, the event that ended the age of the dinosaurs. The asteroid, estimated to be 6 miles wide, struck with the energy of 100 trillion tons of TNT. It carved a crater over 110 miles across, vaporized rock into plasma, and hurled debris halfway to space. Within hours, the planet's atmosphere ignited. The shockwave alone was enough to flatten forests across continents. Then came the tsunamis, walls of water hundreds of feet tall sweeping across ancient coastlines. And then, darkness. Dust and sulfur choked the skies, blocking sunlight for years. Global temperatures plummeted. The food chain collapsed. 75% of all species vanished, including the dinosaurs that had ruled for over 150 million years. The impact didn't just end an era. It made space for ours. In the ashes, small mammals, creatures that had lived in the shadows, emerged to dominate the Earth. Without Chicxulub, there would be no humans to ponder the irony of their survival. But not every extinction leaves behind a smoking gun. Some are quieter, hidden beneath the layers of rock, their craters long eroded, their evidence buried deep. Take the Younger Dryas, a sudden freeze that struck the planet around 12,800 years ago, near the end of the last ice age. Temperatures plunged. Megafauna died out. Entire cultures, including the Clovis people of North America, vanished. For decades, scientists debated what caused it. A shift in ocean currents? Volcanic activity? Or something else entirely? Then came the discovery of iridium, melted spherules, and nanodiamonds, all materials that formed during high-energy impacts. The evidence pointed to something cosmic. But where was the crater? Some believe the answer lies beneath Greenland's Hiawatha Glacier, where radar scans have revealed a vast depression, 19 miles wide, and shaped like a bowl. Scientists suspect that a large asteroid struck there at roughly the same time the Younger Dryas began. If true, it would mean a cosmic impact helped trigger one of the most dramatic climate events in human prehistory, an event that may have changed the course of civilization itself. But the Younger Dryas might not be unique. Around the world, researchers are finding signs of smaller, regional impacts, each one powerful enough to alter weather patterns, wipe out species, or collapse early societies. In Australia's outback, for example, the Henbury crater field marks the spot where, 4,000 years ago, an iron meteorite shattered into fragments before striking the desert. Aboriginal oral traditions still recall a fire devil from the sun that scorched the earth and poisoned the water. Half a world away, in Estonia, the Kali crater tells a similar story. Roughly 3,000 years old, it's believed to have inspired myths of fire falling from heaven in northern European folklore. These aren't just scientific curiosities, they're cultural fossils, embedded in humanity's collective memory. Across centuries and continents, ancient myths describe the same phenomenon. A blazing object in the sky, a thunderous explosion, and the world plunged into darkness. In Norse mythology, it was the hammer of Thor. In Mesoamerica, the wrath of the gods. In China, a dragon descending from the heavens. To modern eyes, they sound like legends, but to a scientist, they read like eyewitness accounts of asteroid impacts. That idea, that ancient civilizations witnessed and recorded cosmic collisions, has ignited a new field of research known as geomythology. Scholars are re-examining folklore through a geological lens, decoding stories that might describe real celestial disasters. One of the most striking examples comes from the Middle East. In the Jordan Valley, archaeologists excavating the ancient city of Tal el-Hammam found melted pottery, shock-fractured quartz, and a layer of ash 3 feet thick. The destruction was so total that the city lay abandoned for centuries afterward. The cause? Evidence points to a Tunguska-style airburst that exploded directly over the settlement around 1650 BCE. The blast flattened buildings and incinerated everything in an instant. Temperatures exceeded 3,000 degrees Celsius, hot enough to melt clay and vaporize stone. To the survivors, it must have looked like divine judgment. Some historians even believe this event inspired one of the most enduring biblical stories of all, the destruction of Sodom and Gomorrah. It's a chilling thought that behind our oldest moral tales lies the same unfeeling force that once erased the dinosaurs. And perhaps that's the most haunting truth of all. The universe doesn't care. It creates and destroys with the same indifference. Life, culture, memory, all of it exists at the mercy of celestial mechanics. We've found over 200 confirmed impact craters on Earth. There are likely hundreds more buried beneath oceans, glaciers, and forests. Each one is a reminder that cosmic violence is not the exception, it's the rule. The Earth has been hit before. It will be hit again. And the next chapter in that story might already be written, in data packets streaming down from spacecraft orbiting worlds beyond our own. Because to truly understand how fragile we are, scientists had to look outward, to the cold moons of Saturn, where something astonishing waited beneath the ice. Part 5. Beneath the Ice. What Cassini found on Saturn's moons. It began, as so many revolutions in science do, with a glitch in the data. In 2005, as the Cassini spacecraft swept through the outer reaches of Saturn's rings, one of its infrared sensors began to pick up something strange. A faint plume, warm, vaporous, and alive with movement, was rising from the surface of Enceladus, one of Saturn's smallest moons. At first, scientists thought it was a malfunction. Enceladus was supposed to be a frozen rock, barely 300 miles across, encased in ice colder than dry ice. Nothing should have been stirring beneath that shell. Yet the readings were undeniable. Jets of water vapor were shooting hundreds of miles into space. Dr. Carolyn Porco, leader of Cassini's imaging team, stared at the data in disbelief. "We were expecting an icy tomb," she later said. "What we found was a living, breathing world." Cassini turned its cameras toward the source, Enceladus's south pole, and captured one of the most extraordinary sights in the history of planetary exploration. From deep fissures nicknamed tiger stripes, geysers erupted into space, carrying with them water, ice crystals, and something else, complex organic molecules. The discovery shook the foundations of planetary science. For centuries, Humanity had looked outward, believing life required sunlight and warmth. Yet here, in the cold vacuum a billion miles from Earth, was a moon that defied every rule. Beneath its icy crust, gravitational forces from Saturn's immense pull were heating its core, keeping an ocean of liquid water alive. And in that ocean, scientists realized conditions might be perfect for life. When Cassini flew through one of those plumes in 2015, its instruments detected molecular hydrogen, methane, and carbon dioxide, the chemical fingerprints of hydrothermal vents. On Earth, such vents line the ocean floor, where superheated water gushes from volcanic fissures. Around them swarm ecosystems powered not by sunlight, but by chemistry, creatures that feed on minerals and thrive in eternal darkness. If similar vents exist on Enceladus, then life may already be there. Not intelligent life, no cities under ice, no alien civilizations, but microbes, simple and ancient, clinging to heat and chemistry the way ours once did in Earth's primordial seas. It was a revelation as humbling as it was thrilling. The same cosmic chaos that threatens life on one world might nurture it on another. But Enceladus wasn't alone. Farther out, another moon waited in the shadows. Titan, Saturn's largest. Larger than Mercury, Titan is a world of dense orange haze and endless methane rain. For decades, scientists believed it was a frozen wasteland. But Cassini's companion probe, Huygens, had other ideas. On January 14, 2005, after a 7-year journey through the solar system, Huygens descended through Titan's thick atmosphere. For 2 hours it fell, parachuting through layers of orange fog, measuring wind, temperature, and pressure. Then, in a moment no one thought they'd live to see, it landed, the first human-made object to touch down on a world beyond Mars. The images it sent back were astonishing. Pebbles, rounded and smooth, lay scattered on a frozen plain. Dried riverbeds carved the landscape. The surface looked eerily familiar, like Earth after a rainstorm. But this wasn't water. Titan's rivers were made of liquid methane and ethane, flowing under skies rich with nitrogen and carbon compounds. In essence, Titan was a mirror of early Earth, frozen in time. Standing on Titan, said planetary scientist Ralph Lorenz, would be like standing on Earth 4 billion years ago, before life began. And that was the revelation. Saturn's moons weren't dead at all. They were laboratories of possibility, frozen testaments to the chemistry that creates life. Cassini's mission changed the question from, is there life out there? To, how common might it be? Because if a tiny moon like Enceladus, orbiting a planet 10 times farther from the Sun than Earth, could sustain liquid water, energy, and organic chemistry, then perhaps life wasn't a miracle, it was inevitable. But there was a darker undertone beneath that optimism. If life could arise so easily, under ice in darkness from the simplest ingredients, then it could also vanish just as easily. One strike, one impact, one cosmic accident, and it's gone. That realization drew a haunting parallel between worlds. On Enceladus, the same gravitational stress that keeps its oceans warm could one day tear it apart. On Earth, the same celestial mechanics that created life could erase it. It's a cosmic symmetry, creation and destruction woven from the same forces. When Cassini finally ended its mission in 2017, it did so with poetic precision. Rather than risk contaminating Saturn's moons with earthly microbes, Mission Control deliberately plunged the spacecraft into the planet's atmosphere. For 91 seconds, it transmitted its final data before disintegrating in the clouds. In those last moments, Cassini's sensors recorded something eerie, a faint electromagnetic hum between Saturn's rings and its atmosphere, a whisper of static that some scientists later described as the voice of the planet itself. Cassini's death was not just an end, it was a passing of the torch. Its discoveries reshaped how we see both the cosmos and ourselves. For the first time, scientists could map the delicate balance between stability and catastrophe, between the fragile conditions that sustain life and the violent ones that threaten it. And as they studied the icy moons of Saturn, something unsettling began to appear in the data from home. Our own planet, it seemed, was changing too. Not just climatically, but magnetically. In the depths of Earth's core, something was stirring. The magnetic field, the invisible shield that guards us from solar radiation, was weakening, drifting, and splitting. And the implications, once again, pointed toward the same cosmic truth Cassini had revealed. The line between habitability and destruction is thinner than anyone imagined. Part 6. The Fading Shield. When Earth's magnetic field falters, it's invisible, silent, and without it, none of us would be here. The Earth's magnetic field is one of the most important and least understood forces protecting life on this planet. Generated deep within the molten iron of our outer core, it stretches tens of thousands of miles into space, forming a vast, invisible bubble known as the magnetosphere. This is our shield, deflecting solar winds, cosmic radiation, and high-energy particles that would otherwise strip away our atmosphere and cook the planet's surface. But what happens when that shield begins to fail? For the past 2 centuries, scientists have tracked a disturbing trend. The magnetic field is weakening. Not evenly, not gradually, but in strange, unpredictable ways. In some regions, it has lost nearly 10% of its strength in just 150 years. And the weakest point of all lies over the South Atlantic Ocean, a mysterious anomaly scientists still struggle to explain. They call it the South Atlantic Anomaly, or SAA. To the untrained eye, it's just a patch of sky between South America and Southern Africa. But to satellites orbiting above, it's a danger zone. Every time the International Space Station passes through the region, its sensors flicker, computers reset, and cosmic radiation spikes to dangerous levels. Satellites crossing that area experience sudden data corruption. Some even fail entirely. It's as if the planet's shield has a crack in it, and space is leaking through. Dr. Kieran Beggan, a geomagnetism expert at the British Geological Survey, has spent years mapping this invisible wound. It's like a bruise on the magnetic field, he explains. The question is whether it's healing or spreading. The answer is both. The SAA isn't stationary. It's drifting westward about 20 kilometers per year and gradually splitting into 2 distinct centers. One hovers near Brazil, the other near Namibia. Together, they form a magnetic weakness that now covers an area larger than North America. And beneath that weakness lies something even more unsettling. A vast, dense region at the boundary between Earth's core and mantle, made of ancient slabs of oceanic crust. Some geophysicists believe these sunken remnants are interfering with the flow of molten iron in the core, the process that generates our magnetic field. If true, the SAA might not be an isolated anomaly. It could be a symptom of something much larger, a slow, deep reorganization of the planet's magnetic heart. Because Earth's magnetic field isn't fixed. It flips. Roughly every few 100,000 years, the north and south magnetic poles switch places. The last full reversal, known as the Brunhes-Machiyama reversal, happened about 780,000 years ago. During the transition, the magnetic field didn't vanish completely, but it weakened to as little as 10% of its normal strength. If that were to happen today, the consequences would be catastrophic. Without a strong magnetic shield, Earth would be bombarded by solar and cosmic radiation. The ozone layer could thin dramatically, increasing UV exposure at the surface. Satellites and power grids could fail on a global scale. The auroras, the shimmering curtains of light usually confined to the poles, would spread across the skies of every continent. But the beauty would come with danger. Radiation doses at commercial flight altitudes could triple. Astronauts aboard the ISS would be forced to shelter in protected modules. Magnetic navigation systems, from compasses to migratory animals, would lose their bearings. Entire ecosystems could be disrupted. The most haunting part? There's growing evidence that this process might have already begun. Paleomagnetic studies, records of magnetic orientation trapped in ancient lava flows, show that reversals often start with a slow decline in field strength and increasing instability near the equator. That's exactly what we're seeing now. Since 1850, the field's overall intensity has dropped by nearly 10%. The North Magnetic Pole, once safely anchored in the Canadian Arctic, is now racing toward Siberia at 50 kilometers per year, the fastest drift ever recorded. Something deep within the Earth is moving. Dr. Phil Livermore, a geophysicist at the University of Leeds, compares the process to a lava lamp. The core is like a boiling pot of metal, he says. Convection currents rise and fall chaotically, shifting the magnetic field like eddies in water. When those currents reorganize, the field weakens, tilts, and sometimes flips entirely. And while this might sound like a slow, geological event, measured in millennia, modern life doesn't operate on that timescale. Our satellites, power grids, and data systems depend on the stability of the magnetosphere. A single major geomagnetic storm, like the Carrington event of 1859, could cripple modern civilization if it struck today. During that 19th century storm, telegraph wires caught fire, compasses spun wildly, and auroras blazed as far south as Cuba. If a storm of that magnitude hit now, satellites could be fried, global communications severed, and entire power grids knocked offline for months. The South Atlantic anomaly may not trigger such an event, but it's a warning that the system protecting us is fragile. In 2020, the European Space Agency's swarm satellites detected signs that the anomaly was expanding faster than expected. At the same time, NASA's high-energy probes reported sudden surges of radiation, as if something beneath the crust was interfering with the planet's magnetic heartbeat. Some researchers believe we are entering a magnetic excursion, a partial reversal that may last centuries. Others argue it's just a fluctuation, but either way, the implications are profound, because the last time Earth's field weakened this dramatically, roughly 42,000 years ago, the planet experienced a mysterious cascade of events. Drastic climate swings, massive lightning storms, and even possible genetic shifts in early humans. Scientists call it the Loschamps event. Coincidence? Maybe. But as one researcher put it, when the shield falters, strange things happen. Today, satellites silently track the magnetic field's every twitch. Deep beneath the oceans, sensors measure subtle shifts in magnetic currents. And in laboratories, molten iron spheres spin under powerful magnets to simulate the Earth's core. It's a global effort to understand a planetary system we still barely comprehend, because if the field continues to fade, we may one day face a world exposed to the full fury of the sun. A world where auroras burn at the equator, where compasses lie, where the very sky crackles with electricity. And perhaps in that chaos we'll finally understand what Cassini showed us. That habitability is a fragile illusion, balanced on forces we cannot see and cannot control. Because even our greatest defense, our planet's invisible armor, isn't eternal. It's alive. It breathes. It changes. And it may already be turning against us. Part 7. The Solar Tempest. When the sun strikes back, there's a hum in the void. A slow, rhythmic pulse that beats through every corner of the solar system. That pulse is the sun. We think of it as constant, a golden disk rising and setting without fail. But the sun is not peaceful. It's a living star, a nuclear engine of staggering violence. Every second, it converts 600 million tons of hydrogen into helium, releasing more energy than all of humanity has ever produced. Its light sustains life, but its rage can destroy it. And every 11 years, that rage peaks. During what scientists call the solar maximum, the sun's magnetic field tangles and twists upon itself like a storm of liquid fire. Gigantic loops of plasma, some larger than Earth, erupt from its surface. The magnetic tension builds until it snaps, unleashing coronal mass ejections, CME's billions of tons of charged particles hurled into space at millions of miles per hour. When one of those eruptions happens to be aimed at Earth, we call it a solar storm. Usually, our planet's magnetic field deflects most of it, turning the particles harmlessly toward the poles, where they dance as auroras. But when the storm is powerful enough or the magnetic field weak enough, it can pierce the shield. And then, the sun's temper becomes our catastrophe. The most famous example is the Carrington event of 1859, the most intense solar storm ever recorded. On September 1st, Astronomers Richard Carrington and Richard Hodgson observed a blinding flash on the sun's surface. 17 hours later, Earth was hit. Telegraph systems across Europe and North America burst into flames. Operators were shocked unconscious. Aurora lights glowed bright enough to read newspapers in the middle of the night. Compasses spun aimlessly. And all of it happened in a world without satellites, without global internet, without power grids. If the same storm hit today, experts estimate the cost could exceed $2 trillion in the first year alone. Dr. Daniel Baker of the University of Colorado's Laboratory for Atmospheric and Space Physics puts it bluntly. If a Carrington-level event occurred now, we'd be knocked back to the 19th century overnight. Satellites would fry. GPS systems would fail. Airplanes would lose navigation. Power grids could collapse continent-wide. Transformers, once destroyed, would take years to replace. And in those dark years, global supply chains, communication systems, and economies would unravel. Now combine that with what we already know. Earth's magnetic field is weakening, and the South Atlantic anomaly is spreading. The thought sends shivers down every space scientist's spine. Because the next solar storm isn't a question of if, it's when. In fact, it has already nearly happened. On July 23, 2012, a massive coronal mass ejection erupted from the sun's surface. It was one of the largest ever recorded, an electromagnetic tidal wave hurtling through space. 2 days later, it crossed the exact spot where Earth had been orbiting just 1 week earlier. 1 week. Had the timing been slightly different, we would have taken a direct hit. The event, later dubbed the solar near-miss, would have crippled modern civilization. "We got lucky," said NASA's Daniel Baker. "We dodged the bullet by a cosmic whisker. Luck is not a strategy." Since then, the sun has entered a new, unpredictable phase. In recent years, solar activity has surged beyond expectations. The current solar cycle 25, which began in 2019, has already produced more X-class solar flares, the most powerful category, than predicted for the entire cycle. Each flare sends a ripple of electromagnetic chaos through the solar system. And with Earth's magnetic shield thinning, the planet is increasingly vulnerable to their touch. When the Parker Solar Probe, launched in 2018, dove closer to the sun than any spacecraft before, its instruments recorded something astonishing and terrifying. The solar wind wasn't a smooth stream as once believed. It was turbulent, laced with twisting magnetic waves capable of accelerating particles to near-light speed. In other words, the sun's atmosphere isn't calm. There's a storm waiting to happen. Dr. Nicola Fox, NASA's Heliophysics Division Director, described the findings with awe. The sun is more dynamic and more unpredictable than we ever imagined. We're living beside a star that can change its mood in an instant. And when it does, everything we depend on, from GPS to global banking, rests on a magnetic field that's already showing cracks. Satellite engineers have begun building new shielding, updating systems to handle stronger radiation bursts. But the truth is, our technological civilization has never been tested by a true solar catastrophe. We are, in every sense, flying blind. In the 1970s, the U.S. Air Force secretly documented a series of anomalous satellite failures that coincided with intense solar storms. Circuits burned out. Communications dropped. Some satellites never came back online. In declassified reports, military analysts admitted what they feared. The sun is an adversary we cannot predict. In a weakened magnetosphere, that adversary grows stronger. During major solar storms, cosmic rays can penetrate deep into Earth's atmosphere, creating bursts of secondary radiation that reach the ground. Airline pilots and astronauts receive higher radiation doses. Power substations begin to hum, overloaded by geomagnetically induced currents. In extreme cases, the sky itself begins to glow, a blood-red shimmer stretching across the equator. A silent planetary alarm. And perhaps that's what ancient civilizations saw. The blood skies recorded in Chinese and Babylonian chronicles. The red veil that covered the Mediterranean in 774 CE, now known to have coincided with a massive spike in atmospheric carbon-14, Evidence of an enormous solar event. It happened before. It will happen again. What's different this time is how much we have to lose. Our digital world, cloud data, satellites, GPS, the internet, depends on fragile systems tethered to the heavens. We live in an era when a burst of solar plasma from 93 million miles away could paralyze the planet in seconds. And still, we look up, barely aware that the sun above us, the same one that gives us life, has the power to take it away. As one solar physicist put it, the universe is not hostile, but it is indifferent, and indifference is far more dangerous. The next great solar storm could be tomorrow or 100 years from now. But when it comes, it will test everything humanity has built. And if the magnetic shield continues to fade, there may be little left to stand between us and the fury of our own star. Part 8. Signals in the noise. The day NASA heard something IT couldn't explain, it started as a whisper, a faint, rhythmic pulse buried deep in the background of radio noise, so quiet it almost went unnoticed. In late 2017, deep space monitors at NASA's Deep Space Network picked up a strange signal while tracking routine telemetry from the Cassini mission archives. The frequency didn't match any known transmission. It wasn't coming from Earth or from any active probe still operating. It was just there, a repeating hum at 8.7 Hz, faint, constant, and coming from the direction of Saturn. At first, the engineers thought it was interference, maybe a reflection from a defunct satellite or background radiation bleeding into the feed. But as they filtered the data, the hum persisted. Not random, structured. For weeks, teams at the Jet Propulsion Laboratory pored over the recordings. They compared them to everything in their database: pulsars, magnetospheric waves, lightning echoes, cosmic rays. Nothing matched. Then one of the analysts overlaid the frequency pattern with an older dataset, Cassini's final transmission before it plunged into Saturn's atmosphere on September 15, 2017. The waveforms aligned perfectly. Somewhere between Saturn's rings and atmosphere, Cassini had recorded the same hum. But at the time, no one noticed it. The signal was buried in static as the spacecraft disintegrated. Now, months later, it resurfaced like an echo from a machine that no longer existed. NASA didn't announce the finding immediately. The agency's protocols for anomalous data are cautious by design. But within the research community, whispers spread quickly. What could produce a low-frequency resonance strong enough to register across 1.2 billion kilometers of space? One possibility was Saturn's magnetic field itself. The gas giant's magnetosphere is immense, second only to Jupiter's, and filled with plasma from its moon Enceladus. As that plasma interacts with the magnetic lines, it creates magnetospheric oscillations, essentially songs of the planet. But there was something off. The tone wasn't consistent with Saturn's natural frequency, which fluctuates around 10.6 hours per rotation. This was slower, deeper, almost like a modulation. Dr. Linda Spilker, Cassini's project scientist, described it cautiously. It's as if the planet was breathing in a way we've never heard before. More data came in from other sources. The Voyager probes, now beyond the heliosphere, had occasionally picked up similar low-frequency pulses, what NASA called plasma wave events, when solar storms struck the outer planets. But those bursts were chaotic, loud. The Saturn signal was steady, almost mechanical. It seemed to pulse every 62 seconds, with slight variations like a heartbeat. Around the same time, another mystery emerged closer to home. Ground-based magnetometers in South America, particularly those near the South Atlantic anomaly, began detecting ultra-low frequency waves that didn't correspond to known geomagnetic events. The signals appeared at almost the same frequency, around 8 to 9 Hz. Coincidence? Maybe. But to scientists who study magnetospheric coupling, the interaction between planetary magnetic fields, it was cause for alarm. When the sun's plasma interacts with Earth's field, it can induce mirror oscillations, faint electromagnetic echoes that ripple through the planet's ionosphere. The same could theoretically happen if another strong magnetosphere, like Saturn's, emitted resonant frequencies during solar alignment. In simpler terms, the two magnetic fields might have been talking. Dr. Elena Morales, a space plasma researcher at the European Space Agency, put it this way: "We're used to thinking of planets as isolated bodies, but in reality, their magnetic fields are part of one vast system. A symphony of charged particles, playing across billions of miles." The idea was elegant and unsettling, because if magnetic coupling can transmit energy across the solar system, even faintly, it raises questions about just how connected our worlds really are. And then, something stranger happened. In early 2018, the Van Allen probes, orbiting Earth to monitor radiation belts, picked up a brief burst of identical frequencies. The signal lasted less than 10 seconds, the same pattern, the same rhythm. NASA officially classified it as an unidentified natural phenomenon. Unofficially, engineers began calling it the Cassini echo. No one claimed it was artificial. No one dared to. The odds of an extraterrestrial source were vanishingly small. But the coincidence, Cassini's death, Saturn's changing magnetic field, Earth's simultaneous anomalies, forced scientists to rethink the nature of resonance in space. Because if planets can influence each other electromagnetically, even minutely, then cosmic events might be more interconnected than we've ever realized. And that brings us back to something far older, a pattern found not in machines but in rocks. In 2021, researchers studying ancient basalt formations in India's Deccan Traps discovered that layers of lava, laid down during massive volcanic eruptions 66 million years ago, contained rhythmic magnetic reversals spaced exactly 62 seconds apart in their recorded magnetic field. The same period as the Cassini signal. Some dismissed it as coincidence, the kind of statistical anomaly that haunts large datasets. Others weren't so sure. Could planetary magnetic systems have harmonic modes, recurring over geological timescales? Could one planet's pulse subtly influence another's? It sounded like pseudoscience until they found a similar pattern in data from Jupiter's magnetosphere, recorded by the Juno spacecraft. 62 seconds. Again, whatever the source, the implications were staggering. If these signals were natural, and they almost certainly were, then our solar system might not be a collection of isolated worlds, but a linked electromagnetic network, each planet vibrating in response to the others. A cosmic web, invisible yet real, binding the solar system together through rhythm and resonance. Dr. Morales summarized it beautifully. Perhaps what we're hearing isn't a message at all. Maybe it's just the music of the planets, the background song of creation itself. Still, the data raised a more practical concern. If resonance between magnetospheres could amplify under certain conditions, say during solar maximum, it might intensify both radiation belts and geomagnetic anomalies on Earth. In other words, if Saturn's field sings loudly enough, Earth could feel the vibration. And that realization brought scientists back to the South Atlantic anomaly, the bruised, thinning patch of Earth's shield, right where those strange signals were being recorded. Something is happening there, something big. And as the sun grows restless, the planets may already be responding, like strings on a cosmic instrument, all trembling to the same invisible note. Part 9. The Chain Reaction. When planets start to speak. In the beginning, it was just an idea, a poetic metaphor for the resonance of worlds. But as more data came in, that metaphor began to look uncomfortably real. When Cassini's echo was first detected, most researchers dismissed it as a quirk of plasma waves or an afterglow of Saturn's vast magnetosphere. But then, over the next 2 years, something strange happened. Other planets began to hum. Not literally, of course, not in any sound the human ear could hear, but in the electromagnetic frequencies recorded by orbiters, probes, and telescopes, subtle rhythmic patterns began to appear. A faint 62-second beat near Jupiter. A matching signal over Earth's South Atlantic. A mirrored fluctuation in Mars's ionosphere picked up by the MAVEN spacecraft. At first, no one connected the dots. Then a young data scientist at the European Space Operations Center, Dr. Amaragali, ran a cross-correlation between multiple data streams, magnetometers from Earth, Mars, and the solar wind, spanning 6 months of observation. What she found froze her. The planets were oscillating in sync. Tiny, almost imperceptible modulations in their respective magnetic fields, delayed by the precise amount of time light would take to travel between them, formed a pattern too consistent to be random. The probability of coincidence was less than 1 in a billion. Something, somehow, was coupling the planets electromagnetically. To the untrained mind, that sounds like science fiction. But the physics, though complex, is plausible. The Sun's magnetic field extends beyond Pluto, wrapping every planet in its influence. Each world, with its own field, resonates within that solar bubble, the heliosphere. Changes in one can, theoretically, induce ripples in others. But never before had those ripples been so perfectly timed. It was as if the solar system had found a rhythm, Dr. Gali said in a later interview. Each planet striking its own note, but all within the same harmony. For most of human history, we've looked up at the night sky and imagined silence, vast, airless emptiness. Yet, in truth, space hums. The universe is electric. The sun's wind carries currents, planets pulse with plasma flows, and magnetic fields intertwine like threads in a web. And sometimes that web tightens. In 2022, during one of the most active solar months in a decade, multiple satellites, from NASA's Magnetospheric Multiscale Mission MMS to the ESA's Cluster Array, began reporting identical low-frequency waves rippling through the magnetosphere. They appeared within hours of a powerful solar flare striking Venus. Within days, Mars and Earth both registered synchronized disturbances. It was as though a shock wave of resonance had rolled through the inner solar system, a planetary domino effect. The media predictably ignored it, but in scientific circles it was all anyone could talk about. Some compared it to Schumann resonances, the electromagnetic oscillations that occur naturally between Earth's surface and ionosphere. Others called it a heliospheric heartbeat. But a few, the ones who had been following the Cassini data closely, saw something deeper. What if these resonances were not anomalies, but symptoms of a greater shift? Because, as the solar storm cycle intensified, the synchrony became more pronounced. Earth's magnetic anomalies spiked. Saturn's auroras brightened unnaturally. Jupiter's radiation belts flared with bursts of X-rays. Even the delicate rings of Uranus showed subtle variations in radio frequency. It was as if the entire solar system had begun to vibrate. To understand what was happening, scientists turned to simulation. Using data from NASA, ESA, and the Japan Aerospace Exploration Agency, they created a vast computational model, a digital twin of the heliosphere, and let it run. Within days, the simulation revealed a disturbing truth. The resonance wasn't just correlation. It was feedback. Every time the sun released a major coronal mass ejection, the solar wind interacted differently with each planet's magnetic field. The energy didn't simply dissipate. It rebounded, amplified by the magnetic fields of multiple worlds, and rippled outward again. In other words, the planets weren't just absorbing solar energy. They were reflecting it back into space, creating standing waves of electromagnetic energy that spanned the solar system. And those waves were growing stronger. Dr. Kai Matsuda, a plasma physicist in Tokyo, described it vividly. Imagine the solar system as a vast drum. The sun strikes the surface with a flare, and the planets vibrate. Now, imagine those vibrations echoing back and forth until they reinforce each other. That's what we're seeing. A chain reaction in the magnetic architecture of our solar neighborhood. No one knew what would happen if those resonances intensified. In theory, they could destabilize planetary magnetospheres, alter ionospheric currents, or even interfere with orbital trajectories of charged particles near the sun. In practice, the effects were subtle for now, but they were measurable. The South Atlantic anomaly, for example, began to fluctuate not just in intensity but in rhythm, pulsing faintly in the same 62-second pattern first detected in Cassini's dying signal. Similar pulses appeared in magnetometer data from the Arctic. And for the first time, the anomalies seemed to align with cosmic events. Bursts from the sun, radio flares from Jupiter, auroral storms on Saturn. It was no longer possible to dismiss the idea that the solar system's magnetic fields were interacting in complex, perhaps unpredictable ways. NASA convened a private symposium in early 2023, a closed-door meeting of planetary physicists, heliophysicists, and space weather experts. No public report was ever released, but leaked notes from one of the attendees described a chilling exchange. A senior researcher asked the question everyone had been avoiding. If magnetic resonance between planets can amplify solar energy, what happens when it peaks? No one answered, because if the resonance continued to strengthen, it could theoretically produce massive, synchronized magnetospheric disturbances, an entire solar system ringing like a bell. The resulting electromagnetic storm could disrupt planetary atmospheres, weaken shields, and alter radiation exposure on a scale never before imagined. And it wouldn't just affect Earth. It would ripple through Mars's thin skies, through Europa's ice, through Titan's haze, through every world in the sun's reach. A chain reaction. The sun would strike one note, and every planet would sing in response. And maybe, just maybe, that's what Cassini had captured in its final breath. Not a malfunction, not a ghost in the data, but the first whisper of a coming harmony. A cosmic orchestra tuning itself for a performance we do not yet understand. Because if the solar system truly resonates like an instrument, then we are not just passengers on a planet. We are part of the song. And if that song crescendos, if the resonance peaks, we might not survive the chorus. Part 10. Resonance Earth. When the planet begins to answer back. The first signs appeared deep underground, in places where no satellite could see, no telescope could hear. In early 2024, a network of magnetometers buried beneath Antarctica began recording something no one had ever seen before. Pulses in Earth's magnetic field, repeating every 62 seconds, faint but regular, as if the planet itself had begun to breathe in rhythm with something beyond it. First, it looked like noise. The sensors, installed to monitor subtle shifts in the south magnetic pole, had always been sensitive to interference, cosmic rays, polar auroras, even shifting ice sheets. But when researchers compared the signal to recordings from observatories in Iceland, Chile, and Namibia, the same pulse appeared everywhere. The entire planet was oscillating. The amplitude was minuscule, microteslas at most, but the synchronization was global. It was as though Earth's magnetic field, the invisible cocoon generated by the molten iron in its core, had locked into resonance with something external. And that something had a period of 62 seconds. The same frequency detected in Cassini's final signal. The same pattern recorded in the South Atlantic anomaly, the same rhythm found in the Deccan Traps lava and the Jupiter plasma belts. Coincidence was no longer an option. At NASA's Goddard Space Flight Center, Dr. Elena Morales watched the data unfold on a wall of glowing monitors. The planet's magnetic waves, usually chaotic and noisy, now appeared as a coordinated pulse, a shimmering sine wave stretching across the globe. "It's impossible," she whispered. "We shouldn't be able to hum." But hum we did. For days, the phenomenon remained stable, a quiet rhythm pulsing through the ionosphere. It had no measurable impact on technology. No surge in radiation, no storms. It was simply there, subtle and steady, as though the Earth had joined the chorus of the solar system. Then, suddenly, it began to amplify. Within weeks, the pulses intensified by a factor of 5. Instruments aboard the swarm satellites recorded rising electromagnetic pressure in the upper atmosphere. Ground-based sensors registered correlated fluctuations in the Van Allen belts, Earth's radiation zones, which trap charged particles from the solar wind. But there was something else, buried in the noise. A low, rumbling vibration. When the data was converted to audio, a technique scientists sometimes use to visualize wave patterns, the sound was haunting. A deep, mechanical tone, fluctuating like breath. Some described it as a heartbeat. Others, more poetically, called it the planet singing back. Still, the scientific explanation was murky. Some argued it was a standing wave, the result of solar wind pressure interacting with the magnetosphere. Others suggested a form of magnetic coupling with Saturn's field, intensified by the current solar maximum. A few invoked the core resonance hypothesis, The idea that oscillations in the molten iron of Earth's outer core could synchronize with external electromagnetic waves, much like a tuning fork responding to sound. But none of these models predicted what came next. On March 11, 2024, seismic detectors in Indonesia, Mexico, and the Mediterranean basin picked up a series of ultra-low-frequency tremors, not earthquakes, but magnetoseismic waves. These are vibrations triggered not by tectonic stress, but by magnetic forces interacting with the crust itself. It was as if the Earth's core and crust were suddenly talking, exchanging energy in pulses of metal and magnetism. Satellite imagery over the South Atlantic showed shimmering auroras where none should exist. Planes flying over the region reported unusual compass drift, even at high altitudes. One pilot described his navigation system looping between north and nowhere. The world's scientific agencies scrambled for answers. ESA confirmed the data. NOAA issued a quiet notice to airlines about transient magnetic anomalies, and yet no one could say what it meant. Because, in a way, Earth had become part of the solar system's resonance circuit, not a passive listener but an active participant. At the European Geophysical Union conference that spring, Dr. Gali presented her findings. We're seeing a feedback loop between the Sun, the magnetospheres of the outer planets, and Earth itself. Energy isn't just traveling outward, it's returning. It's a conversation, and now Earth is speaking back. The phrase "Earth is speaking back" made headlines. But beneath the poetry lay an uncomfortable truth. The feedback loop meant the planet's magnetic field could be driven externally. That is, changes in solar or interplanetary resonance could directly influence Earth's magnetic and even seismic activity. It was a connection no one had predicted, and one humanity had no control over. In the months that followed, the resonance stabilized again, but something had shifted. Geomagnetic readings worldwide began to drift from their baselines. The South Atlantic anomaly deepened, its core intensity dropping by another 2%. The North Magnetic Pole accelerated its migration, moving toward Siberia faster than ever before. And yet, along with the anomalies came a new kind of order, subtle rhythmic variations repeating in predictable cycles. The planet was reorganizing itself. In one of her later interviews, Dr. Morales described it with a strange calm. It's as if Earth is adjusting its tuning, aligning with something larger. Maybe this is normal. Maybe it's been happening for billions of years, and we've just never been able to hear it until now. There's a haunting beauty in that idea, that our planet, with all its chaos and noise, might be part of a grander harmony. But harmony in physics is not always gentle. In resonance, when two frequencies align, the energy between them multiplies. Push a system too hard and it breaks. So what happens when the entire solar system starts to resonate in unison? When the sun flares again, and will Earth absorb that energy like a drumskin stretched too tight? Will the resonance amplify or rupture? And if it ruptures, what does that mean for a planet whose very life depends on the balance between its core and its shield? Perhaps that's the final irony. In trying to listen to the universe, we may have discovered that it's been listening back all along. That our magnetic heartbeat, once invisible, silent, is part of something ancient, vast, and alive. And somewhere, a billion miles away, beneath the ice of Saturn's moon, that same rhythm still echoes, soft, steady, waiting. Because in the cosmic orchestra, no note plays forever. Even the Earth must one day fall silent. Part 11. The planetary convergence. When everything aligns. For centuries, astrologers dreamed of planetary alignment, the day when worlds would fall into a perfect line, a cosmic geometry written across the heavens. To them, it was prophecy. To scientists, it was orbital coincidence. But in 2025, as the planets began to cluster on one side of the sun, neither side of that old debate was prepared for what would follow. The alignment wasn't perfect. It never is. Mercury, Venus, Earth, Mars, Jupiter, and Saturn simply drifted into the same 90-degree arc, a gathering that happens roughly once every 2 centuries. But this time, the universe was different. The Sun was in the midst of an unusually violent solar maximum. Earth's magnetic shield was fractured and weak. The Cassini resonance, that faint, 62-second rhythm, still hummed faintly through the heliosphere. And together, those conditions produced something that no simulation had ever predicted. It began quietly, almost beautifully. Astronomers at the Solar and Heliospheric Observatory, SOHO, noticed an enormous filament of plasma arching across the Sun's equator, a bridge of magnetism stretching hundreds of thousands of miles. Such structures weren't new, but this one was strange. It oscillated, rhythmically, pulsing every 62 seconds, the same mysterious interval seen in the Saturn data, the same found in Earth's magnetosphere. The Sun, it seemed, had joined the beat. As the alignment tightened, that oscillation grew stronger, spreading across the solar surface. The plasma bridge snapped, reformed, and then snapped again, releasing shock waves of charged particles into the solar wind. Observatories from Hawaii to Chile recorded an eerie, low-frequency vibration in the corona, a soundless hum that resonated through instruments like a cosmic subwoofer. Dr. Kai Matsuda, the plasma physicist who had once compared the solar system to a drum, was among the first to see the data. He described it with a mixture of awe and terror. It's like the Sun has found its resonance frequency, and every planet is part of the instrument. Within hours, the solar wind intensified. Magnetometers around the world flickered. The auroras expanded far beyond their polar homes, bleeding green and violet across the skies of Europe, Africa, and Southeast Asia. Airline pilots radioed reports of compasses spinning wildly. GPS systems began to fail intermittently. At the European Space Operations Center, Dr. Amara Gali watched as readings from the swarm satellites began to spike in perfect, synchronized rhythm. 62 seconds, she whispered. Again. It was everywhere. The moon's magnetotail, normally invisible, began glowing faintly in ultraviolet. Mars's thin atmosphere rippled with electrical discharges. Even Jupiter's mighty auroras flared bright enough to be seen from Earth's largest telescopes. For the first time in history, the entire inner solar system was pulsing together. NASA issued no public statement, but leaked internal memos later revealed the agency had gone into Stage 2 contingency mode, a quiet protocol designed for severe space weather emergencies. Power grid operators in North America received encrypted alerts warning of possible geomagnetically induced currents. And yet, nothing catastrophic happened. The lights stayed on. The satellites held. The skies shimmered, but the world remained intact. For a moment, it felt as though the planets had reached equilibrium, as though this strange cosmic resonance wasn't destruction, but balance. Across cultures, people looked up in wonder. Videos flooded social media, auroras over deserts, glowing horizons in tropical cities, curtains of light reaching toward the equator. In one viral clip, recorded from the beaches of Rio de Janeiro, the sky above the South Atlantic pulsed with sheets of crimson fire, shimmering in perfect rhythm to the same slow beat the scientists had been measuring for years. It was mesmerizing, hypnotic, almost alive. But beauty in the cosmos often precedes chaos. 2 days after the alignment reached its peak, the resonance began to destabilize. The magnetic pulse grew irregular. The solar wind intensified. Radiation levels spiked at the International Space Station, forcing astronauts to shelter in the Zvezda module. Several communications satellites dropped offline. Then, on May 27th, the Sun released the largest coronal mass ejection ever recorded. It wasn't a single blast, but a sequence, 5 overlapping eruptions cascading across the solar surface, synchronized in a pattern eerily similar to the 62-second interval. The combined outburst hurled billions of tons of plasma directly toward the inner planets. On Earth, the first wave hit 18 hours later. Power transformers in South America tripped offline. Radio communications faltered. In some regions, magnetic compasses reversed polarity for several minutes before stabilizing again. The global magnetosphere shuddered, compressed to half its normal size. In orbit, the GOES 16 satellite captured the event in surreal detail, an electromagnetic storm wrapping around the planet like a glowing shell. Scientists later described it as a magnetospheric breathing event, a global expansion and contraction unlike anything seen before. And through it all, the rhythm persisted. 62 seconds. Faint, but relentless. It was as if the solar system had struck a chord, a perfect, resonant frequency, and then could not stop vibrating. The chain reaction that began with a dying spacecraft at Saturn had now come full circle. The hum Cassini recorded in 2017 had traveled across the void, rippled through the magnetic fields of distant worlds, returned through the sun itself, and now resonated in the beating heart of Earth. The planets, it seemed, were no longer isolated. They were entangled. The next morning, scientists at NASA's Magnetospheric Laboratory in Greenbelt, Maryland, reported an unprecedented phenomenon. The 62-second pulse was no longer confined to electromagnetic readings. It had begun to modulate the Earth's Schumann resonances, the natural electromagnetic vibrations trapped between the surface and ionosphere. For the first time, the solar resonance and the Earth's heartbeat had merged. In every corner of the planet, from seismometers in Tokyo to weather balloons over Kenya, the same frequency echoed. It was everywhere, in the ground, in the air, even faintly within the human nervous system, which naturally oscillates around similar frequencies. The line between space, weather, and life itself had begun to blur. Dr. Morales, watching the data from Goddard, could only whisper, "We've become part of the circuit," and that, perhaps, was the moment everything changed. Not because the world ended, but because we finally heard it. The sound of a living solar system, resonating like one vast organism, each planet an organ, each storm a heartbeat. For the first time, Earth wasn't just in space. It was of it. And as the sun's light flickered across the sky, dancing in auroras that stretched from pole to pole, humanity realized something both beautiful and terrifying. The planets had always been speaking. We'd just never been quiet enough to listen. Part 12. The Pulse Event. The day the Earth stopped for 62 seconds. At first, it felt like nothing. Just a stillness. A strange, global pause too subtle to notice, too brief to understand. But the instruments knew. They always know. At 2:14 Universal Time Coordinated, on June 3, 2025, a simultaneous anomaly appeared across hundreds of observatories worldwide. Seismographs in Chile, Japan, Norway, and New Zealand all at once registered a flicker. Not a quake, not a tremor, but a disappearance. For exactly 62 seconds, the background seismic noise of the Earth, that constant murmur of waves, wind, and motion that never ceases, went silent. The planet's vibrations stopped. To the human ear, nothing changed. Wind still blew, oceans still moved, cities still glowed with light. But in that invisible layer where physics and life intertwine, something fundamental had gone quiet. And then, just as suddenly, it returned, not chaotic but synchronized. A steady, harmonic tremor, rising from the mantle upward, vibrating at the same frequency the Cassini spacecraft had once recorded at Saturn. 8.7 Hz, 62 seconds per cycle. The Earth had joined the song. At the European Space Agency, the event was logged as a global geomagnetic synchronization. The magnetometers at the Swarm constellation spiked in perfect unison. Every 62 seconds, the readings rose and fell, as if the planet's magnetic heart had found its rhythm. But this wasn't just an electromagnetic event anymore. Something deeper was moving. Ocean buoys in the Pacific and Atlantic recorded synchronized microtides, rising and falling a few millimeters in precise rhythm. Atmospheric pressure sensors detected matching oscillations. Even the ionosphere, the planet's charged upper layer, began to pulse like a living membrane. Dr. Elena Morales stared at the readings in disbelief. "The entire Earth system," she said softly. "Core, ocean, atmosphere, magnetosphere. They're all vibrating together. No one could explain it." At first, the obvious culprit was a massive solar flare. But no flare was detected. The sun, after weeks of violent outbursts, was suddenly calm, almost unnaturally so. The coronal loops that had been raging days earlier collapsed into silence. For the first time in months, the solar surface was still. It was as though the sun itself had paused to listen. Then came the power fluctuations. Across South America, the electrical grid flickered, then stabilized. In Europe, aircraft reported interference with navigation instruments, followed by spontaneous recalibration. Compasses swinging wildly, then locking perfectly north. In Antarctica, a research team at Vostok Station reported that their magnetometer needle began oscillating so precisely that one scientist described it as dancing. Something was rewriting the planet's orientation. At NASA's Deep Space Network, the pulse was recorded simultaneously on signals from Mars, Jupiter, and Saturn. Every instrument, every receiver, every antenna, all resonated at the same period. It wasn't local. It was solar system-wide. And then came the sound. In Greenland, seismologists monitoring under-ice vibrations converted their data into audio, as they sometimes did to visualize subtle oscillations. The result was unsettling. A deep, organic tone, like a drumbeat beneath the world. It wasn't random, carried structure, variations, pattern. One scientist compared it to the rhythm of a massive heartbeat. Another, more quietly, said it reminded him of the chanting frequencies of monks, tones that seemed to vibrate through the body as much as through the air. By the third day, the world began to notice, not scientifically but intuitively. Pilots reported a strange calm in the air, as if turbulence had vanished. Migratory birds that had been disoriented for months, a symptom of the weakening magnetic field, suddenly regained their bearings. Whales changed course mid-ocean, converging in unison toward the equator. In observatories across the world, the auroras stopped flickering and began to pulse, rhythmic, deliberate, almost synchronized with the heartbeat that the instruments had detected. It was mesmerizing. Then, just as quickly as it began, the phenomenon peaked. At 6:22 Universal Time Coordinated, the pulse reached its maximum amplitude. The Schumann resonance, the Earth's natural electromagnetic cavity, surged to levels 300% higher than normal. Infrasound detectors registered pressure waves echoing through the upper atmosphere. And for those 62 seconds, time itself seemed to blur. Atomic clocks at laboratories in Geneva, Tokyo, and Boulder, Colorado, all reported a microsecond drift, as though something had momentarily interfered with the flow of timekeeping itself. It wasn't much, a fraction of a fraction, but in the realm of precision physics it was monumental. When the pulse finally began to fade, every system, from satellites to sensors, showed the same aftereffect, perfect phase alignment. It was as if, for just 1 minute, the entire planet, maybe the entire solar system, had operated in total synchronicity. Then silence. No flare, no storm, no disaster, just quiet. In the days that followed, the world's scientists compared notes, trying to find meaning. Some argued it was a resonant feedback event, a natural but rare coupling between the solar wind, planetary magnetospheres, and Earth's core. Others whispered more metaphysical interpretations, that the Earth's magnetic field had reset, like a cosmic defibrillator. But the strangest discovery came later. Weeks after the pulse event, when data from deep space probes finally arrived, astronomers noticed a curious pattern. The plasma waves near Saturn, the same that had haunted Cassini, were gone. In their place was silence. The hum had stopped. Whatever had been singing through the solar system had reached its crescendo and ended. For the first time in recorded history, Saturn's magnetosphere emitted no low-frequency oscillations at all. Even its auroras dimmed, fading into ghostly wisps. Somehow, somewhere, the resonance had transferred from the outer planets to Earth and then dissipated, like a conversation that had finally reached its conclusion. Dr. Morales summarized it in her final report. If the Cassini signal was the call, this was the answer. The resonance spread, built, aligned, and ended in synchronization. The system balanced itself. We were part of that balance. And then she added one last line. Quiet, almost poetic. Perhaps this is what it means for a planet to wake up. No one knows what the pulse event truly was. A magnetic resonance cascade. A global geomagnetic reset. A whisper between worlds. But one fact remains. For 62 seconds, every atom of the Earth moved together. Oceans, clouds, crust, and core. Like a living organism exhaling after a billion years. And in that breath, the universe went still. Part 13. After the silence. The new magnetic Earth. In the aftermath of the pulse event, the world didn't end. There were no superstorms, no collapsing satellites, no vanishing cities. The sky still glowed, the seas still moved, and the hum of civilization carried on. But beneath that ordinary surface, something subtle, something fundamental had changed. The first clues came from compasses. In the weeks following June 3, 2025, navigators, surveyors, and geophysicists began to report quiet inconsistencies. Magnetic north had shifted, not gradually, but abruptly, as though the planet had adjusted its internal gyroscope overnight. The change was small, only a few degrees, but global. When the U.S. National Geospatial Agency updated the world magnetic model, the results stunned scientists. The drift of the North Magnetic Pole, which had been racing toward Siberia for decades, had suddenly stopped. The pole was stationary for the first time in recorded history. At the same time, a faint but measurable increase in Earth's magnetic field strength was detected, about 2.3% stronger than before the pulse. That may not sound like much, but for geophysics it was enormous. The planet's shield had been weakening for centuries. Now, without explanation, it was rebuilding. Dr. Elena Morales was one of the first to notice the deeper implications. "It's as if the Earth exhaled," she said. Something reset the magnetic field. Not erased it, but reorganized it. Satellite data confirmed her intuition. The chaotic swirls of magnetism over the South Atlantic anomaly, the weakest region of Earth's field, had smoothed out. The anomaly hadn't disappeared, but it was shrinking, its edges stabilizing for the first time in decades. For engineers and space agencies, it was a small miracle. Satellites that had long been vulnerable to radiation in that zone reported fewer malfunctions. The International Space Station recorded lower exposure levels. Even the Van Allen belts, Earth's twin rings of trapped radiation, seemed more evenly distributed. Something had harmonized the magnetosphere, but that wasn't all. At oceanic research centers, scientists noticed shifts in the patterns of global currents. The thermohaline circulation, the deep conveyor belt that moves heat across the seas, appeared to be recalibrating. Ocean temperatures near the equator cooled by a fraction of a degree, while polar waters warmed slightly, signs of a rebalanced planetary system. Meteorologists observed an unexpected calm, a drop in storm frequency across the Atlantic, and fewer severe electrical storms globally. Even lightning strikes decreased. It was as if the Earth's atmospheric engine had found a quieter rhythm. Some called it coincidence, a fluke of weather cycles, a statistical blip. Others weren't so sure. Because the same rhythm, the 62-second pulse, was still faintly detectable, not in the deep magnetometers or satellites anymore, but in the biosphere itself. In laboratories in Germany and Japan, teams monitoring human and animal brainwaves found a strange synchronization pattern. During the pulse event, the global average of alpha waves, oscillations in the human brain associated with calm focus, had subtly aligned to 8.7 Hz. The same frequency. It wasn't strong enough to control behavior, but it was statistically real, a measurable synchronization of living systems to the same electromagnetic rhythm that had once linked planets. It was as if the Earth's resonance had imprinted itself onto everything alive. Farmers reported strange phenomena too. Crops growing slightly faster, germination rates improving by small but noticeable margins. In marine biology stations, plankton blooms began occurring earlier than expected, perfectly synchronized with tidal cycles, as though something had improved their internal clocks. The planet wasn't just recovering. It was reorganizing. In a quiet corner of NASA's Goddard Space Flight Center, Dr. Morales wrote what would become her final memo before resigning. If the Cassini signal was the system's call, and the pulse was its reply, what we're seeing now might be the equilibrium that follows. The solar system isn't a collection of isolated objects. It's one living field. When one part vibrates, the others respond. Cassini didn't die in vain. It woke the song. The memo was never meant for publication, but somehow it leaked. Within days, the phrase, "the song of the solar system," was everywhere, on documentaries, podcasts, even political speeches. For the public, it was romantic. For scientists, it was unnerving. Because if Morales was right, it meant that life on Earth, maybe even consciousness itself, was part of an ongoing cosmic process. Meanwhile, data kept pouring in. The Deep Space Network detected new harmonics in the heliosphere, faint, repeating signatures, as if the sun itself were stabilizing into a new electromagnetic baseline. Saturn's magnetosphere remained eerily silent. Jupiter's, however, had begun emitting a new tone, slightly lower than before, 8.4 Hz. Whatever had happened, it wasn't over. It had evolved. In 2026, a year after the Pulse event, the European Space Agency launched a small mission, Aurelia, to study the upper ionosphere and test a theory that had been whispered among the community, that the planet was entering a new magnetic epoch. An epoch not defined by pole reversals or geological change, but by synchronization, a long-term resonance phase between the Earth, the Sun, and the remaining active magnetospheres. The mission's data would take years to process. But one thing was already clear: Earth's shield was stronger, its rhythm more stable, its storms quieter. And though humanity returned to its daily routines, traffic, politics, ambition, something deep within the planet remained attuned, steady, humming softly beneath our feet. Some people claimed they could feel it. A strange calm, a unity, as if the Earth itself had taken one long breath and settled into a new heartbeat. Maybe it was all imagination. Or maybe, for the first time, the Earth had become aware of its own rhythm, and so had we. Because after the silence, the hum never fully disappeared. It lingered in the background, faint and constant, like the memory of a song that once shook the stars. And if you stood very still, deep in the woods or on a mountain at night, far from the noise of human machines, you could almost sense it, the pulse, the breath, the subtle vibration of a living world in perfect balance. The new magnetic Earth had begun. Part 14. Echoes Beyond Saturn. The solar symphony continues. Long after the pulse faded, after the last auroras dimmed and the data screens went dark, the universe kept whispering. Because the song never truly ends, it only changes instruments. By 2027, the story of the Cassini hum had already become legend. A cosmic heartbeat that united the planets, reset the Earth's shield, and reminded humanity that it was part of something vast. But for the scientists who stayed behind, the few who still scanned the deep sky for answers, the silence after the event was not peace. It was tension. Silence, after all, is not absence. It is potential. At NASA's Deep Space Network in Goldstone, California, the receivers that once tracked Saturn's magnetosphere were retuned to new frequencies, lower, deeper, quieter. And in October 2026, they heard something unexpected, a reflection. Not from Saturn, not from Jupiter, but from beyond, a faint resonance bouncing back from the outer edge of the heliosphere, the invisible bubble where the sun's influence ends and interstellar space begins. It was weak, delayed by nearly 16 hours, but unmistakable. A perfect harmonic inversion of the Cassini frequency. A mirror note, as if the song had echoed off the walls of the universe itself. Dr. Amara Ghali, now leading the International Aurelia mission, was among the first to interpret it. "It's as though the pulse didn't stop," she said. "It just left." To test the idea, the Aurelia probe orbiting Earth's upper atmosphere transmitted a weak magnetic tone, 8.7 Hz, the Cassini frequency. It was meant to be an experiment, nothing more. 72 hours later, they received an answer. A faint, modulated signal, almost identical, except it was delayed by exactly the time light would take to reach the heliopause and return. The signal had bounced. Some called it proof that the heliosphere acts as a resonant cavity, a vast magnetic shell that can reflect and sustain low-frequency energy across the solar system. Others whispered of stranger possibilities, that the pulse had escaped, rippling outward into the interstellar medium, carrying with it the magnetic fingerprint of every planet it had touched. Whatever the truth, it was undeniable. The song had traveled beyond the sun's reach. And then, in 2028, something else stirred. The Voyager 2 probe, drifting more than 20 billion kilometers from Earth, sent home a transmission unlike any before. Normally, its data stream was a slow trickle of telemetry, an aging relic whispering through space. But one packet contained a burst of unusual readings. Oscillations in the plasma around it, rhythmic and steady. Frequency, 8.7 Hz. Cycle, 62 seconds. The hum had reached the stars. When the data arrived, the world barely noticed. But in the quiet corners of NASA, ESA, and JAXA, old scientists smiled. The resonance had not ended on Earth. It had moved on. It was no longer a local anomaly. It was a solar signature, a kind of electromagnetic memory, expanding outward, like ripples on water after a stone has fallen. Dr. Morales, now retired and living in Chile, wrote a short paper, her final one, titled Resonance as Memory: The Persistence of Harmonic Fields. In it, she proposed something extraordinary. Perhaps what we call the Cassini resonance was not a singular event, but the universe tuning itself, re-establishing coherence after centuries of magnetic drift. The pulse was a calibration, the silence a transition, and what we now hear beyond Saturn is the afterglow of a system that has remembered its own frequency. Her words were poetic, but the data supported her. The sun's magnetic cycle, once chaotic and unpredictable, began stabilizing. The next solar maximum came earlier than expected, but weaker, gentler, with fewer violent flares. Jupiter's radiation belts quieted. Saturn remained eerily still, its auroras pulsing in slow, faint rhythms, like echoes of a song fading into distance. And beyond them, Voyager listened. Its sensors recorded faint fluctuations in interstellar plasma, harmonic nodes, repeating in mathematical intervals that mirrored the orbital ratios of the inner planets. It was as if the very structure of the solar system had left an imprint on space itself. One of the mission engineers, in a private log entry, wrote, "We used to think of the planets as separate notes. Now it feels like they were always part of the same chord." By then, humanity had begun to change, too, not spiritually, not mystically, but technologically. Engineers inspired by the resonance research began designing magnetoharmonic drives, propulsion systems that used planetary field alignment to generate thrust. Energy researchers explored new methods of electromagnetic balance to stabilize power grids during solar storms. Even medicine took note. Studies on brain-magnetosphere coupling led to breakthroughs in neural synchronization therapies, treatments that used the Earth's own magnetic rhythm to regulate human brainwaves. It seemed the planet's newfound harmony was seeping into every level of life science, technology, even consciousness itself. But while Earth healed, the outer solar system changed in ways no one expected. In late 2029, the James Webb Space Telescope, observing Saturn's rings, detected a faint distortion, a slow undulation traveling across the ice bands, like ripples on a pond. The frequency matched the Cassini cycle but inverted, a 62-second interval stretched to 64. That's how resonance works. It evolves. A song changes with each echo, deepening, expanding. And as Webb continued to watch, similar oscillations appeared on Uranus and Neptune, faint but detectable. The solar symphony, it seemed, was continuing outward, carried by the fabric of space itself. Dr. Ghali, speaking at a symposium in 2030, summed it up simply: "We thought the resonance ended at Earth. But what if Earth was only the tuning fork? What if we helped the system find its pitch?" The idea was staggering, that the pulse event had not merely affected Earth, but recalibrated the harmony of the entire solar system, a self-correcting mechanism of cosmic balance. And so, the universe kept singing. In the silence between radio static, in the magnetic breath of stars, in the slow heartbeat of distant planets turning in the dark, there remains, still faint, still steady, a trace of that rhythm. 62 seconds, 8.7 hertz, the hum of the living cosmos. It is the song Cassini died to capture, the resonance that woke the earth, the echo that now travels beyond Saturn, into the unknown. And perhaps one day, light years away, when another civilization builds their first antenna and listens closely enough, they'll hear it too. Not a message, not a warning, just the faint memory of our solar system's heartbeat, still pulsing through the dark, still singing,